What if I told you that somewhere in the vast expanse of the universe, there exists a place so cold it defies imagination, and another so hot it could vaporize entire planets in an instant? The universe is a place of extremes where the rules of physics are pushed to their absolute limits, and the records it holds are nothing short of mind-bending. Welcome to a journey through the most extreme records in the universe, where we'll uncover the most astonishing, awe-inspiring, and downright bizarre phenomena that exist beyond our world. From the fastest objects racing through the cosmos at unimaginable speeds to the largest structures ever discovered, stretching across billions of light years, these records aren't just fascinating, they're windows into the very fabric of reality. They challenge our understanding of science, spark our curiosity, and remind us just how small we are in the grand scheme of things. But why should we care about these cosmic extremes? Because they reveal the universe's secrets, showing us how it works, how it began, and perhaps even how it might end. They inspire us to dream bigger, to explore further, and to question everything we think we know. So, are you ready to dive into the most extreme corners of the cosmos? From the hottest places to the coldest, the brightest objects to the darkest mysteries, this video will take you on a journey that will leave you in awe of the universe's boundless wonders. Stay tuned, because by the end of this, you'll see the universe in a whole new light. Let's begin. Now, turning to the concept of speed in the cosmos, let's explore the fastest objects in the universe. Imagine something so fast it could circle the Earth 7 times in just 1 second. Sounds impossible, right? Yet in the universe, such speeds are not only possible, they're happening right now. The fastest known objects are particles accelerated to nearly the speed of light by cosmic events like supernova or the immense gravitational pull of black holes. These particles, often protons or electrons, travel at speeds so extreme that they challenge everything we know about physics. Take cosmic jets, for example. These are streams of particles ejected from the regions around black holes or neutron stars, racing through space at close to the speed of light. The energy required to propel these particles is staggering, and the forces at play are beyond anything we can replicate on Earth. These jets can stretch for thousands of light years, illuminating the cosmos with their incredible speed and power. But how do these particles reach such velocities? It all comes down to the extreme environments they originate from. Black holes, for instance, have gravitational fields so strong that they can accelerate particles to nearly the speed of light as they spiral inward. Similarly, supernova, the explosive deaths of massive stars, release so much energy that they can hurl particles across the universe at breakneck speeds. These events push the boundaries of our understanding, forcing scientists to rethink the laws of physics as we know them. What's even more fascinating is that these ultra-fast particles aren't just a curiosity, they play a crucial role in shaping the universe. They carry energy across vast distances, influence the formation of galaxies, and even impact the cosmic microwave background, the faint afterglow of the Big Bang. By studying these particles, we gain insights into the fundamental forces that govern the cosmos. So, the next time you look up at the night sky, remember that somewhere out there, particles are racing through the void at speeds that defy imagination. These cosmic speedsters are not just breaking records, they're helping us unravel the mysteries of the universe itself. And as we move forward, we'll explore even more extreme phenomena that will leave you in awe of the cosmos's boundless wonders. Now, turning to the vastness of the cosmos, let's shift our focus to the largest known structure in the universe, the Hercules-Corona Borealis Great Wall. This colossal formation is so immense that it defies comprehension. Stretching across an astonishing distance of approximately 10 billion light-years, it holds the record as the largest single structure ever discovered in the observable universe. To put that into perspective, if you were to travel at the speed of light, it would take you 10 billion years to cross from one end to the other. That's more than half the age of the universe itself. The Hercules-Corona Borealis Great Wall was discovered by astronomers analyzing data from gamma-ray bursts, which are incredibly energetic explosions that occur in distant galaxies. These bursts act like cosmic flashlights, illuminating the structure of the universe on the largest scales. By mapping the locations of these bursts, scientists noticed an unusual concentration in a specific region of the sky, revealing the existence of this gigantic wall of galaxies. What makes this structure so remarkable is not just its size, but what it tells us about the universe. The Hercules-Corona Borealis Great Wall challenges our understanding of how matter is distributed in the cosmos. According to the cosmological principle, the universe should appear roughly the same in all directions on large scales. However, the existence of such a massive structure suggests that the universe might not be as uniform as we once thought. This discovery has sparked debates among scientists, pushing them to reconsider the fundamental principles that govern the cosmos. Visualizing the scale of this structure is almost impossible, but imagine a tapestry woven from billions of galaxies, each containing hundreds of billions of stars. This wall isn't just a random collection of galaxies, it's a cosmic web, a network of filaments and clusters that trace the underlying structure of the universe. Simulations and galaxy maps help us grasp its enormity, showing how galaxies are strung together like beads on an invisible thread, forming a pattern that stretches across unimaginable distances. The Hercules-Corona Borealis Great Wall is more than just a record-breaking structure, it's a window into the universe's past and a clue to its future. By studying it, we gain insights into how galaxies form, how matter clumps together over time, and how the universe evolved from the Big Bang to the present day. It reminds us that even in the vastness of space, there are patterns and structures that connect everything from the smallest particles to the largest walls of galaxies. As we continue our journey through the most extreme records in the universe, this discovery serves as a humbling reminder of just how much we have yet to learn. The cosmos is full of surprises, and each one brings us closer to understanding the grand tapestry of existence. Now turning to the depths of cosmic extremes, let's explore the most massive black hole ever discovered, Ton 618. This colossal black hole is a true titan of the universe, with a mass estimated to be around 66 billion times that of our Sun. To put that into perspective, if you were to stack 66 billion suns together, you'd still only begin to grasp the sheer enormity of this gravitational monster. Ton 618 is not just a black hole, it's a supermassive black hole, a category of cosmic giants that dominate the centers of galaxies. But how do we measure something so massive and so far away? Astronomers use a combination of techniques, including studying the motion of gas and stars around the black hole. As these objects orbit the black hole, their speeds reveal the immense gravitational pull at work. In the case of Ton 618, the surrounding gas emits intense radiation as it spirals inward, creating a bright quasar that can be observed from billions of light years away. This quasar acts as a beacon, allowing scientists to calculate the black hole's mass and understand its properties. The impact of Ton 618 on its surroundings is nothing short of extraordinary. Its gravitational influence shapes the entire region, pulling in matter and energy at an astonishing rate. The accretion disk, a swirling ring of gas and dust spiraling into the black hole, reaches temperatures of millions of degrees, emitting vast amounts of light and radiation. This process not only powers the quasar, but also influences the formation and evolution of galaxies in its vicinity. Supermassive black holes like Ton 618 play a crucial role in the life cycle of galaxies. They are thought to reside at the heart of nearly every large galaxy, including our own Milky Way. As these black holes grow, they regulate the growth of their host galaxies by releasing energy that can heat up or expel gas, preventing the formation of new stars. In a way, they act as cosmic regulators, balancing the birth and death of stars and shaping the structure of the universe on the grandest scales. The discovery of TON 618 challenges our understanding of how such massive black holes form and grow. Current theories suggest they start as smaller black holes that merge and accumulate matter over billions of years. However, the sheer size of TON 618 raises questions about whether there's a limit to how large a black hole can become. It also highlights the incredible diversity of black holes, from stellar mass black holes formed by collapsing stars to these supermassive behemoths that anchor entire galaxies. As we continue to unravel the mysteries of the universe, TON 618 stands as a testament to the extremes that exist beyond our world. It reminds us that even in the darkest corners of space, there are forces at work that shape the cosmos in ways we are only beginning to understand. With each discovery, we gain a deeper appreciation for the intricate and awe-inspiring nature of the universe. Now turning to the fiery extremes of the cosmos, let's explore the hottest places in the universe. At the top of this scorching list are the cores of massive stars where temperatures can soar to unimaginable heights. In these stellar furnaces, nuclear fusion reactions generate temperatures reaching up to 100 million degrees Celsius. To put that into perspective, that's more than 6,000 times hotter than the surface of our Sun. These extreme conditions are what allow stars to shine brightly, converting hydrogen into helium and releasing vast amounts of energy in the process. But the heat doesn't stop there. When a massive star exhausts its fuel, it undergoes a cataclysmic explosion known as a supernova. In the aftermath of such an event, temperatures can spike even higher, reaching up to 1 billion degrees Celsius. This incredible heat is generated as the star's core collapses and its outer layers are violently ejected into space. The shock waves from a supernova can heat surrounding gas and dust to extreme temperatures, creating a glowing remnant that can be observed for thousands of years. Another contender for the title of the hottest place in the universe is the environment around supermassive black holes, particularly in their accretion disks. As matter spirals into these cosmic giants, friction and gravitational forces heat the material to temperatures exceeding tens of millions of degrees. This process produces intense radiation, including X-rays, which can be detected by telescopes here on Earth. The combination of extreme heat and powerful magnetic fields in these regions creates some of the most energetic phenomena in the universe. The conditions that create such extreme heat are as fascinating as the temperatures themselves. In the cores of stars, the immense pressure and density force atomic nuclei to collide and fuse, releasing energy in the form of heat and light. In supernova, the sudden release of gravitational energy during the collapse of a star's core drives temperatures to staggering levels. And around black holes, the sheer force of gravity accelerates matter to incredible speeds, generating heat through friction and collisions. These extreme temperatures not only shape the universe but also play a crucial role in the creation of elements. The intense heat and pressure in stellar cores and supernova are responsible for forging heavy elements like iron, gold, and uranium. Without these fiery cosmic events, the building blocks of planets and even life itself would not exist. As we continue to study these extreme environments, we gain a deeper understanding of the forces that govern the universe. From the cores of stars to the remnants of supernova, these scorching hotspots remind us of the incredible energy and power that exist in the cosmos. They challenge our imagination and push the boundaries of what we thought was possible, revealing a universe that is as dynamic as it is awe-inspiring. Now turning to the other end of the temperature spectrum, let's explore the coldest place in the universe, the Boomerang Nebula. Located approximately 5,000 light-years from Earth, this cosmic wonder holds the record for the lowest natural temperature ever recorded, dipping to just 1 degree above absolute zero. Absolute zero, the theoretical point where all molecular motion stops, is -273.15 degrees Celsius. To put that into perspective, the coldest temperature ever recorded on Earth was -98.6 degrees Celsius in Antarctica. The Boomerang Nebula is so cold that it even outpaces the background temperature of space itself, which hovers around -270 degrees Celsius. So how does the Boomerang Nebula achieve such extreme cold? The answer lies in its unique structure and the behavior of its central star. The nebula is what astronomers call a protoplanetary nebula, a phase in the life cycle of a star similar to our Sun. As the star ages and exhausts its nuclear fuel, it begins to shed its outer layers, creating a cloud of gas and dust that expands outward. In the case of the Boomerang Nebula, this expansion is happening at an astonishing rate, about 164 kilometers per second. This rapid expansion causes the gas to cool dramatically, much like how a can of compressed air feels cold when released. The result is a nebula that acts as a natural cosmic refrigerator, chilling its surroundings to near absolute zero. The Boomerang Nebula's cooling mechanism is further enhanced by its shape. The nebula's distinctive bow tie or boomerang-like appearance is created by the outflow of gas being funneled into two opposing jets. This structure allows the gas to spread out and cool more efficiently, creating the frigid conditions that make it the coldest known place in the universe. Observations using powerful telescopes like the Atacama Large Millimeter Array have revealed intricate details of this process, showing how the gas flows and cools as it moves away from the central star. The extreme cold of the Boomerang Nebula also has fascinating implications for our understanding of the universe. It challenges our assumptions about the limits of temperature and the behavior of matter under such conditions. For example, at temperatures close to absolute zero, gases can exhibit strange quantum behaviors such as forming Bose-Einstein condensates, a state of matter where particles act as a single quantum entity. Studying the Boomerang Nebula helps scientists explore these phenomena and refine their understanding of the laws of physics. As we marvel at the Boomerang Nebula's icy depths, we're reminded of the incredible diversity of environments in the universe. From the scorching cores of stars to the frigid expanses of this cosmic refrigerator, the extremes of temperature reveal the dynamic and ever-changing nature of the cosmos. These records not only push the boundaries of our knowledge, but also inspire us to keep exploring the mysteries that lie beyond our world. Now turning to the brightest objects in the universe, let's dive into the fascinating world of quasars. These cosmic powerhouses are not only the most luminous objects known, but also some of the most enigmatic. A quasar, short for quasi-stellar radio source, is essentially the intensely bright core of a distant galaxy, powered by a supermassive black hole at its center. But what makes quasars so incredibly bright? The answer lies in the immense energy released as matter spirals into the black hole, heating up to extreme temperatures and emitting light across the electromagnetic spectrum. Quasars form when a supermassive black hole, often billions of times more massive than our Sun, begins to consume vast amounts of gas, dust, and even stars from its surrounding environment. As this material falls toward the black hole, it doesn't just disappear. Instead, it forms a swirling disk of superheated matter called an accretion disk. The friction and gravitational forces within this disk generate enormous amounts of energy, causing it to glow with a brilliance that can outshine entire galaxies. In fact, some quasars are so luminous that they can be seen from billions of light years away, making them visible even in the early universe. The energy output of a quasar is staggering. A single quasar can emit thousands of times more energy than an entire galaxy containing hundreds of billions of stars. To put this into perspective, if a quasar were placed at the center of our Milky Way, its light would outshine the Sun by a factor of trillions, making it impossible to miss even from the farthest reaches of our galaxy. This incredible luminosity is what makes quasars such valuable tools for astronomers. They act as cosmic beacons, helping scientists study the structure and evolution of the universe, especially during its early stages. But quasars aren't just bright, they're also incredibly dynamic. The intense radiation and powerful jets of particles they emit can have a profound impact on their host galaxies. These jets, which can extend for thousands of light years, can heat up surrounding gas, trigger star formation, or even suppress it, depending on the conditions. This interplay between quasars and their environments plays a crucial role in shaping the evolution of galaxies over billions of years. Interestingly, quasars also provide a window into the past. Because light takes time to travel across the vast distances of the universe, observing a quasar means we're seeing it as it was billions of years ago. This allows astronomers to study the conditions of the early universe and understand how galaxies and black holes have evolved over time. Quasars are like time capsules, preserving the history of the cosmos in their brilliant light. As we marvel at the sheer brilliance of quasars, we're reminded of the incredible forces at work in the universe. These luminous giants not only illuminate the depths of space, but also challenge our understanding of physics and the limits of energy. From their formation to their impact on the cosmos, quasars stand as a testament to the dynamic and ever-changing nature of the universe. And as we continue to study them, they offer new insights into the mysteries that lie beyond our reach. Now turning to the oldest known objects in the universe, let's explore the Methuselah star and ancient galaxies that offer us a glimpse into the earliest chapters of cosmic history. These celestial relics are like time travelers, carrying the secrets of the universe's infancy. The Methuselah star, officially known as HD 140283, holds the record as one of the oldest stars ever discovered, with an estimated age of around 14.5 billion years. That's older than the universe itself, according to some estimates, which has led to fascinating debates among scientists. So, how do astronomers determine the age of such ancient objects? For stars like Methuselah, they analyze the amount of certain elements such as hydrogen and helium, as well as heavier elements like iron. Stars formed in the early universe had very low amounts of these heavier elements, which were created later through stellar processes. By measuring these elemental abundances, scientists can estimate a star's age. In the case of Methuselah, its composition suggests it was born in a time when the universe was still in its infancy, making it a living fossil of cosmic history. Ancient galaxies, on the other hand, provide another window into the early universe. These galaxies, some of which formed just a few 100 million years after the Big Bang, are observed using powerful telescopes like the Hubble Space Telescope and the James Webb Space Telescope. By studying the light from these galaxies, astronomers can determine their distance and consequently their age. The light from these ancient galaxies has traveled for billions of years to reach us, allowing us to see them as they were when the universe was young. What do these ancient objects tell us about the early universe? They reveal a time when the cosmos was much denser and hotter, filled with the first generation of stars and galaxies. The Methuselah star, for instance, challenges our understanding of stellar formation and the timeline of the universe's evolution. Its age suggests that the first stars may have formed earlier than previously thought, prompting scientists to refine their models of cosmic history. Ancient galaxies, meanwhile, show us how the universe transitioned from a dark, featureless expanse to a vibrant tapestry of stars and galaxies. They provide clues about the processes that drove the formation of the first structures in the universe, such as the role of dark matter and the reionization of hydrogen gas. By studying these galaxies, astronomers can piece together the story of how the universe evolved from its chaotic beginnings to the ordered cosmos we see today. As we reflect on these ancient objects, we're reminded of the vastness of time and the incredible journey the universe has taken. The Methuselah star and ancient galaxies are not just relics of the past, they are keys to understanding the origins of everything we see around us. They challenge our assumptions, inspire new questions, and deepen our appreciation for the dynamic and ever-changing nature of the cosmos. And as we continue to explore these ancient wonders, we uncover more about the universe's earliest moments and the forces that shaped its destiny. Now turning to the most dense objects in the universe, let's explore the incredible world of neutron stars. These cosmic powerhouses are the densest known objects, packing an unimaginable amount of mass into a tiny space. To put it into perspective, a single teaspoon of neutron star material would weigh billions of tons on Earth. That's like squeezing the mass of a mountain into a space no bigger than a sugar cube. But how do these extreme objects come to exist? Neutron stars are born from the dramatic deaths of massive stars. When a star many times more massive than our Sun exhausts its nuclear fuel, it collapses under its own gravity and explodes in a supernova. What remains after this cataclysmic event is a neutron star, a core so dense that protons and electrons are crushed together to form neutrons. This process creates an object with a diameter of only about 12 miles, yet with a mass 1 to 2 times that of our Sun. The physics behind this transformation is as bizarre as it is fascinating, challenging our understanding of matter and gravity. The composition of neutron stars is equally mind-bending. Their interiors are thought to consist of a superfluid core, where matter behaves like a frictionless liquid, surrounded by a solid crust made of atomic nuclei and free electrons. The pressure inside a neutron star is so intense that it creates conditions unlike anything we can replicate on Earth. Scientists speculate that the core might even contain exotic states of matter, such as quark-gluon plasma, where the fundamental building blocks of protons and neutrons break down into their constituent particles. But the strangeness doesn't end there. Neutron stars are also known for their extreme magnetic fields, which can be trillions of times stronger than Earth's. These magnetic fields power some of the most energetic phenomena in the universe, such as pulsars rapidly spinning neutron stars that emit beams of radiation like cosmic lighthouses. When two neutron stars collide, the resulting explosion, known as a kilonova, releases an immense amount of energy and creates heavy elements like gold and platinum, scattering them across the cosmos. Studying neutron stars not only reveals the limits of physics, but also helps us understand the universe's most extreme environments. Their formation, composition, and behavior provide clues about the nature of matter under conditions we can only imagine. As we continue to observe these cosmic marvels, we uncover more about the forces that shape the universe and the incredible processes that occur within it. And with each discovery, we're reminded of just how extraordinary the cosmos truly is. Now turning to the most energetic events in the universe, let's dive into the explosive phenomenon of gamma-ray bursts. These are the most powerful explosions ever observed, releasing more energy in just a few seconds than our Sun will emit over its entire 10 billion-year lifetime. To put it simply, a single gamma-ray burst can outshine an entire galaxy for a brief moment. But what causes these colossal bursts of energy? Gamma-ray bursts originate from some of the most violent events in the cosmos. The two main types are long-duration bursts, which last more than 2 seconds, and short-duration bursts, which are over in less than 2 seconds. Long bursts are thought to occur when massive stars, many times larger than our Sun, collapse at the end of their lives, forming black holes. As the star's core collapses, it triggers a supernova explosion, and jets of energy are launched at nearly the speed of light. These jets, packed with gamma rays, are what we detect as gamma-ray bursts. Short bursts, on the other hand, are believed to result from the collision of two neutron stars or a neutron star merging with a black hole. When these incredibly dense objects spiral into each other, they release a tremendous amount of energy in the form of gamma rays. The collision also produces gravitational waves, ripples in space-time that scientists can detect with advanced instruments like LIGO and Virgo. These events not only create gamma-ray bursts but also forge heavy elements like gold and platinum, scattering them across the universe. The energy released in a gamma-ray burst is almost beyond comprehension. In just a fraction of a second, these bursts can emit as much energy as a supernova, but concentrated into a narrow beam. This beam is so intense that if one were to occur within a few thousand light-years of Earth, it could strip away our planet's ozone layer, leading to catastrophic consequences for life. Fortunately, gamma-ray bursts are extremely rare in our galaxy, and most occur billions of light-years away. Scientists study gamma-ray bursts using satellites equipped with gamma-ray detectors, such as NASA's Fermi Gamma-Ray Space Telescope. These instruments allow us to observe the bursts in real time and gather data about their origins and effects. By analyzing the light and energy from these events, researchers can learn more about the extreme conditions that produce them and the role they play in shaping the universe. Gamma-ray bursts are not just cosmic fireworks, they are windows into the most extreme environments in the universe. They challenge our understanding of physics, energy, and the life cycles of stars. As we continue to study these incredible events, we uncover more about the forces that drive the cosmos and the incredible processes that occur within it. And with each discovery, we're reminded of just how dynamic and awe-inspiring the universe truly is. Now turning to the most distant known objects in the universe, let's explore the farthest reaches of what we can observe. These objects, often galaxies or quasars, are located at the very edge of the observable universe, billions of light-years away from Earth. They are like cosmic time capsules, offering us a glimpse into the universe's earliest days. But how do we measure such unimaginable distances, and what do these distant objects tell us about the universe's expansion? To determine the distance to these far-off objects, astronomers rely on a phenomenon called redshift. When light travels through the expanding universe, its wavelengths stretch, shifting toward the red end of the spectrum. The greater the redshift, the farther away the object is. This stretching of light is a direct result of the universe's expansion, a discovery made by Edwin Hubble in the 1920s. By measuring the redshift of a galaxy or quasar, scientists can calculate how far away it is and how long its light has been traveling to reach us. One of the most distant objects ever observed is a galaxy known as GNZ 11. Located approximately 13.4 billion light-years away, this galaxy existed when the universe was just 400 million years old, a mere toddler in cosmic terms. Observing GNZ 11 is like looking back in time to an era when the first galaxies were forming, and the universe was still in its infancy. The light we see from GNZ 11 today began its journey long before Earth even existed. Quasars, the incredibly bright cores of distant galaxies powered by supermassive black holes, also hold records for distance. The most distant quasar discovered so far, named J03131806, is located more than 13 billion light-years away. Its light reveals a universe that was just 670 million years old, a time when the first stars and galaxies were beginning to illuminate the cosmos. These quasars are not only distant but also incredibly luminous, outshining entire galaxies despite their immense distance. Studying these distant objects provides crucial insights into the universe's expansion and evolution. The light from these galaxies and quasars carries information about the conditions of the early universe, such as the density of matter and the rate of star formation. By analyzing this light, scientists can test theories about how the universe has grown and changed over billions of years. For example, observations of distant objects have helped confirm that the universe's expansion is accelerating, driven by a mysterious force known as dark energy. To observe these distant objects, astronomers use powerful telescopes like the Hubble Space Telescope and the James Webb Space Telescope. These instruments are equipped with sensitive detectors that can capture the faint light from galaxies and quasars billions of light-years away. Deep field images, which focus on a small patch of sky for extended periods, reveal thousands of galaxies, each at a different stage of cosmic history. These images are like windows into the past, allowing us to piece together the story of the universe's evolution. The most distant known objects in the universe are more than just scientific curiosities. They are keys to understanding the cosmos. They show us how the universe has expanded over time, how galaxies have formed and evolved, and how the first stars and black holes came into existence. As we continue to push the boundaries of observation, we uncover more about the universe's origins and its ultimate fate. And with each discovery, we're reminded of the vastness of space and the incredible journey of light across billions of years to reach us. Now turning to the conclusion of our journey through the most extreme records in the universe, let's take a moment to reflect on the incredible phenomena we've explored. From the fastest objects racing through the cosmos to the largest structures stretching across unimaginable distances, each record has revealed a new layer of the universe's complexity and grandeur. These extremes are not just fascinating facts, they are windows into the fundamental forces and processes that shape everything around us. We've marveled at the most massive black holes, whose gravitational pull bends space and time, and the hottest places in the universe where temperatures reach millions of degrees. We've shivered at the thought of the coldest regions where atoms nearly come to a standstill, and been dazzled by the brightest objects whose light outshines entire galaxies. We've peered back in time to the oldest known objects, witnessing the universe in its infancy, and studied the densest objects where matter is packed so tightly that a teaspoon would weigh billions of tons. And we've stood in awe of the most energetic events whose power rivals that of entire stars. These records are more than just milestones, they are clues to the universe's deepest mysteries. They challenge our understanding of physics, push the boundaries of technology, and inspire us to ask bigger questions. What lies beyond the observable universe? How did the first stars and galaxies form? What is the true nature of dark energy and dark matter? Each discovery brings us closer to answering these questions, but also reveals how much we have yet to learn. As we continue to explore the cosmos, these extreme records remind us of the universe's vastness and our place within it. They show us that the universe is a place of endless wonder, where the rules of physics are stretched to their limits and beyond. And they inspire us to keep looking, keep questioning, and keep dreaming. So, what do these extremes mean for the future of space exploration and science? They remind us that the universe is full of surprises waiting to be uncovered. They challenge us to build better telescopes, develop new theories, and push the boundaries of human knowledge. And they invite us to imagine what other records might be out there, waiting to be discovered. If you've enjoyed this journey through the most extreme records in the universe, don't forget to share your thoughts in the comments below. What record fascinated you the most? What cosmic mystery do you hope we'll solve next? And if you want to explore more cosmic wonders, be sure to subscribe and hit the notification bell so you never miss an update. The universe is vast and the journey is just beginning. Let's keep exploring together.